In this next module, I'm going to talk about the alternative tests that you can use instead of the t-test and ANOVA when you violate the assumptions of t-test and ANOVA. These are called non-parametric tests. I'm going to be talking in this module about Wilcoxon sign rank, Wilcoxon rank sum, and Kruskal-Wallis test. These are all what are called non-parametric statistics, and all we mean by non-parametric is that we're not estimating any parameters. So when you do a t-test or an ANOVA, you're estimating the means in those different groups and the standard deviations in those different groups. We're not going to be estimating any parameters like that in the Wilcoxon and the Kruskal-Wallis test. We're just going to get a p-value at the end of the day, so there won't be any estimation involved, only hypothesis testing. So I'll start here with the Wilcoxon rank sum test, because actually in the very first week of this course we saw a Wilcoxon rank sum test. So I'm going to use that same example now. The Wilcoxon rank sum test is used as the alternative to the two-sample t-test when you have a small sample and you have a non-normally distributed outcome. So if you have a small sample and it looks like your outcome variable is not normally distributed, you might choose to, instead of running a t-test, to run a Wilcoxon rank sum test. Remember that we had this hypothetical weight loss trial that I showed you in the very first week of the course. 10 dieters were randomized to follow diet 1, and 10 dieters were randomly assigned to follow diet 2. Group 1 lost an average of 34.5 pounds. Group 2 lost an average of 18.5 pounds. And you might just look at those numbers and think that diet 1 is better. The mean is higher. The mean weight loss is higher in group 1. That would be a natural conclusion. But let's look at the data more closely. When you look at the histogram for diet 2, it turns out that the mean was a loss of 18.5 pounds. The median is a loss of 19 pounds. It's a pretty even, it's not exactly a normal curve, but might be close to enough to a normal distribution. However, when you look at the histogram, the raw data from diet 1, it turns out that there was one person in that group of 10 who lost 300 pounds. So the mean weight loss was huge, 34.5 pounds, but that's mostly driven by that one person. The median loss was only 4.5 pounds. If you were to look at these data and were to analyze these data using a two-sample t-test, you would not find a significant difference between the groups. Now let's look at the raw data. Here's diet 1. We can actually look at the numbers because there's only 10 people on each diet. Here's the weight loss in pounds, the change in weight in pounds. So for example, one person gained 4 pounds, one person lost 300 pounds. That's for diet 1. For diet 2, here are the changes in weights. You'll notice that if you look at the raw data, there's a much more consistent weight loss in diet 2. If I were going to be recommending a diet 2 patients, it seems like everybody in diet 2 lost a pretty good chunk of weight. Whereas diet 1, it was much more variable. One person did great, but there were a lot of people who didn't do as terrific on diet 1. So if I'm looking at the data now, I might just intuitively, instinctively think, well, diet 2 seems somewhat better. We can actually apply a statistical test to evaluate which diet is better. We're going to apply something called the Wilcoxon rank sum test. It's also sometimes called the Mann-Whitney U test. I prefer the term Wilcoxon rank sum test because rank sum test tells you exactly what it does. You rank the data and then you sum them. So we want to know if there's a difference in weight loss between the two diets. The outcome variable is weight change. It's a continuous variable. However, it is not a normally distributed variable. If you look at those histograms, there's a huge left tail for diet 1. So it might have been normally distributed, but we had that one outlier which made it a non-normal distribution. We have a small n, only 10 in each group, so we have to worry about the normality assumption here. A t-test is not going to be appropriate here. It's also not going to be appropriate to just throw out the one person who lost a lot of weight in diet 1, because that person's a real person who lost a lot of weight. We want to give them some credit for that. So we don't want to just throw out that outlier. But the Wilcoxon rank sum test can keep the outlier in. Are the observations correlated? No, we have independent groups here. Are groups being compared? Yes. And how many are being compared? There's 2 groups. Normally we would, if it weren't for the violation of the normality assumption, we would be doing a two-sample t-test. But because we violated the normality assumption here, our outcome variable is not normally distributed, and we have small n, we're going to choose for the Wilcoxon rank sum test. Again, another, this is also called the Mann-Whitney U test. Those are equivalent. So the first step of the rank sum test is just to rank the data. We're going to take everybody, and we're going to ignore the group they're in for the moment. We're going to order the diets, order the weight losses ignoring diet. So we're going to order from the worst weight loss to the best weight loss. The person who lost the least is the person who gained 4 pounds. They get a rank of 1. The person who did the best, the person who lost 300 pounds, they get a rank of 20. And then we rank everybody else in between. Again, ignoring groups. So the ranks, both groups can have both sets of ranks. You'll notice just looking at the ranks that the most of the high ranks go to diet 2. So we rank the data, ignoring which group people are in, from the lowest to the highest, 1 to 20. Notice that we are including the person who lost the 300 pounds. They're getting the highest credit. They're getting that highest rank of 20. But the difference between 19 and 20 is much, much smaller than the difference between -30 and -300. So that outlier is not having so much influence here. By looking at ranked data, we're essentially comparing the medians rather than comparing the means. We then sum the ranks within each group. So we're going to sum the ranks for group 1, comes out to be 73. We're going to sum the ranks for group 2, that comes out to be 137. The one with the bigger sum of the ranks is going to be the better diet. What the Wilcoxon rank sum test then does is it looks at those sums of the ranks and tells you whether or not they're statistically different. This is a little tricky if you have different sample sizes. Right? What if one group only had 5 people and the other group had 20 people? Well, of course, the sum of the ranks is going to be higher for the bigger group. So the Wilcoxon rank sum test accounts for differences in sample sizes as well. Here we have the same sample size. We just need to answer the question, is 137 statistically different than 73? And in fact, when we apply that test, it does turn out that the p-value here comes out to be statistically significant. It actually shows us that diet 2 is superior to diet 1, despite the fact that the mean weight loss was higher in diet 1. So by applying the correct statistical test here, we are able to say that diet 2 is superior. I'm not going to go into the nitty-gritty details of the actual mathematical calculations of distinguishing that 73 from that 137. If you want the details on that, there is an optional material on that for you. I now want to briefly review the Wilcoxon sign rank test. This is the non-parametric alternative to the paired t-test. Recall that we talked last week about a randomized trial of DHA oil to treat eczema. Here's a table, a figure from that trial. I showed you part B from that trial last week. There was a bunch of p-values on this figure, and you can see where did those p-values come from. Well, these are showing the p-values for whether or not the placebo group and the DHA group, the control group and the DHA group, whether or not their SCORAD scores went down at all a significant amount over time. So all of the p-values I've circled here came from Wilcoxon sign rank tests. So when you're doing a within group comparison over time, those p-values come from the Wilcoxon sign rank test. Here we were comparing only week 0 to week 8, so we're actually only comparing 2 time points. The SCORAD index, the SCORAD score, turns out to be non-normally distributed. Our sample size was small here. We only have 53 people, so we're going to want to use a non-parametric equivalent to the paired t-test rather than use the paired t-test. So again, how did I get there? I wanted to know whether or not the patients improved in SCORAD score from baseline to 8 weeks, just 2 time points. The outcome variable is SCORAD, this severity score of eczema. It is a continuous variable, but it is not normally distributed, and we have small numbers, so we cannot apply a t-test here. Are the observations correlated? Yes, it's the same people before and after, so we also have correlated data here. So we would normally do a paired t-test, but because we violated the normality assumption, we're going to use the non-parametric equivalent to the paired t-test, which is the Wilcoxon sign rank test. There's only 2 time points being compared, which is why we can use a paired t-test or a Wilcoxon sign rank test. The mechanics of the Wilcoxon sign rank test, just briefly, it's very similar to the Wilcoxon rank sum test. It's going to involve some ranking, except this time instead of we're going to be looking at the signs rather than 2 groups. So you're going to calculate the change in SCORAD score for each participant. So just like we do for the paired t-test, everybody has an improvement score, a change score. You then rank the absolute values of the changes in SCORAD score from the smallest to the largest. So the person who had the biggest absolute change would get the biggest rank. We're ignoring sign for the minute. The null hypothesis here is that there's no change. We're ignoring sign for the minute. We would then add up the ranks, sum up the ranks from the people who improved. That's the people who would have a negative sign. and we would add up the ranks from the people who got worse. That's the people who had a positive sign. So that's where the sign part comes in. We're comparing people who improved to people who got worse. Does either sum of the ranks dominate? The Wilcoxon sign rank test compares these values to determine whether the improvements significantly exceeded the declines or vice versa. Remember, the null hypothesis here is that there's no change. So we just want to know if there's a significant change in either direction, either going up or going down. If under the null, you'd expect the sum of the ranks to be about equal for the negatives as for the positives. If you violate the null, if you reject the null, that would suggest that there was either a significant improvement or a significant decline. And all we're asking in this particular example is whether or not there was a significant improvement over time in the DHA group alone or in the control group alone. So, and we saw that indeed these p-values, the p-value for the DHA group from the Wilcoxon sign rank test, that p-value comes from the Wilcoxon sign rank test, that came out significant. The p-value from the Wilcoxon sign rank test applied just to the control group did not come out significant. So the within group change was significant for the DHA group, but not significant for the control group. But the p-value that really mattered here is not the within group changes, but the p-value we should have cared about here is the between group difference. Did the DHA group improve more than the control group? To get that p-value, we had to apply a Wilcoxon rank sum test, the between group, to compare the two groups in their improvement in score-add scores, and that came out to be non-significant. So as we said, even though the within group improvement is significant in one group but not the other, that doesn't mean the between group differences are going to be significant, and they weren't here. All of those were done, all those p-values though were done by non-parametric tests because the score-add score is not normally distributed. Finally, if you want to compare two or more groups, more than two groups, and you have a non-normally distributed outcome variable, the non-parametric equivalent to the ANOVA is something called the Kruskal-Wallis test. And it basically, I'm not going to go over the mechanics because it basically works in the exact same way as the Wilcoxon rank sum test. You're going to rank everybody, ignoring group, and then you're going to sum up the ranks within the groups and somehow